Okay, let me briefly go over, what was covered in chapter 1, heat transfer. First, we studied there are three different heat transfers: conduction, convection, and radiation. So the first one is Q by conduction, the second one is Q by convection, the last one is Q by radiation. Then what is the governing equation for each heat transfer? The first one, for conduction heat transfer, we can use Fourier's law. Then what is Fourier's law? Minus Ka dt over dx. That's how you determine the rate of heat transfer by conduction. And we are going to study this equation in very detail in chapter 3 and chapter 5. What about convection heat transfer? We can use Newton's law of cooling, H times 8 times delta T, temperature difference. We are going to study this equation in very detail in chapter 7, 8, and 9. And today we are going to briefly go over how do we calculate the radiation heat transfer. We can use Stefan Boltzmann's law, which is epsilon times the surface area times the temperature to its fourth power. So that's how you determine the radiation heat transfer. This one is a Stefan Boltzmann constant. It is 5.677 times 10 to minus 8. This is the surface area of the source of the radiation. So if you want to determine the radiation heat transfer from the sun, that area is going to be total surface area of the sun. Then what is this T? T is going to be the surface temperature of the source of the radiation. So if you want to talk about the solar radiation, this T is going to be the effective surface temperature of the sun, which is 5,777 Kelvin. Okay. That's the rate of heat transfer from the sun. What about the rate of heat transfer from any surface? Not every surface can emit the radiation at the same rate. Some surface can emit radiation very well, and some surfaces cannot emit radiation, that much. So there is a, property. There is a parameter that differentiate, the which one can emit radiation better than the other. That is called emissivity epsilon. Oh, that's a sigma epsilon. So this epsilon has a value between 0 and 1. So 1 means this this surface can emit radiation as much as the ideal surface. 0 means the surface cannot emit radiation. This is a surface property. So this emissivity depends on the surface of the source of the radiation. So that's everything. That's the governing equation for radiation. When we have a time later, right before final exam, then we are going to go over we are going to use 1 or 2 less time to discuss how we determine radiation. Okay? So that's everything about the introduction to heat transfer. Then let's talk about how to study conduction heat transfer. Yes. That's a surface property. So some surface can emit radiation as much as the sun. Like this, the whiteboard can emit radiation very well. Or this, this wall can also emit radiation very well. But it's material property. It is not related to, the color or, anything. It is a material property and the surface roughness. Okay? No, not necessarily. Okay, that actually require, some more information. I can spend maybe 10 minutes to show you how this emissivity is going to work. So let's say that there's a surface. This is the surface where, the radiation occurs. So let's say there's an incoming radiation. So there is a sun smiling on a sunny day. Then what do we expect? When there is a sunny day, if you're standing in the parking lot and looking at the sun, what do you expect? You're receiving radiation from the sun, right? It's hot. When you look at the sun, don't look at the sun, use that, the sunglasses, and you can feel that there's a heat coming from the sun. That's a radiation. So when there's a radiation coming from the sun to the surface, there are three, the phenomena we can expect. The first, the radiation heat transfer can be observed. And two, that can be reflected like a mirror. That can be transmitted like a glass. So there are three phenomena. One, reflected. Two, observed. Three, transmitted. Then when it reflects, there is no heat transfer to the surface. So the temperature of the surface does not change. When it is observed, then there is a heat transfer into the surface, so there is a temperature increase. When it is transmitted, there's nothing happen, on the surface, so it doesn't matter. Those reflected is called rho. Those observed is alpha. Those transmitted is going to be tau. So when you calculate the sum of these three, alpha plus rho plus tau should be 1. So when there is an incoming radiation, it should be either observed, transmitted, or reflected. Okay? Now, most surfaces are not transparent. So unless it's a clear glass, we usually neglect tau. Most likely, we don't expect transmission because most, the surfaces are not transparent. Can you see, the people on the other room? No, we can because it's not transparent, right? So usually there's no tau. So when we talk about how the surface respond to the incoming radiation, it's going to be either observed or reflected. Observed or reflected should be 1. Now, for thermal equilibrium, whatever observed should be the incoming radiation should be the same as outgoing radiation to maintain thermal equilibrium. So what is incoming radiation for this surface? This alpha, right? And what is outgoing radiation? This rho? No, this is just the reflection of incoming radiation. The sun can emit radiation. What about this surface? The surface can also emit radiation. That is radiation emitted by its own surface. This is epsilon. And to have a thermal equilibrium, this alpha should be the same as epsilon. Then let me go back. You said those meters can reflect the incoming radiation very well, right? So if it is meter, what is rho? Almost 1, right? When you have a meter, it can reflect the sunlight. So you can say the reflection rho is going to be almost 1. When the reflection is close to 1, what is the alpha? how much radiation can be observed if it is a meter? Almost zero, near zero. Then how much emission this meter can release? Almost zero. So those surfaces which can reflect the sunlight very well cannot emit radiation very well. Make sense? Then, what is the total radiation from this surface to the outside? There are two. One is the reflected incoming radiation, rho, and its own radiation, epsilon. So rho plus epsilon together is called radiosity. So this is the total radiation from this surface. The radiation that can be created by its own surface plus the radiation reflected, from the incoming radiation. Together is going to be radiation from a surface. Okay? I know it sounds a little bit complicated, right? By the way, just for one more information, it's very interesting. This alpha, how much radiation can be observed, how much radiation can be reflected, how much radiation can be transmitted, are wavelength specific. Then what is wavelength? These are wavelength specific. So what kind of, what type of radiation exists? There will be visible light, infrared, and ultraviolet, X-ray, gamma, etc., etc., etc. Even so, there are many different types of radiation. And when we talk about thermal radiation, we consider three major radiations. They are UV, ultraviolet, visible light, and infrared. So those three. And how can we know one is UV and another is visible light? The last one is infrared. Based on their wavelength. So usually, visible light has a wavelength between 0.3 micrometer to 0.7 micrometer. So here we have red, yellow, and etc., etc., and finally purple at the end. I can combine red and blue together, purple. So these are visible lights based on wavelength. Do you remember, when you were high school or middle school, you use this, the triangle, the glass, trying to, make a rainbow. When wavelength is less than 0.3 micrometers, UV light. Even less than that, X-ray. Even less than that, gamma, and all the, the crazy things. What about wavelengths greater than 0.7? Infrared. If you have a campfire, on the parking lot, don't do a campfire in parking lot, but let's assume that there is a free park and you do a parking, the campfire, and when you look at the campfire, you feel that it's hot. Why is that? Because there's an infrared coming from the fire to you, whose wavelength is greater than this one. Then, when a surface can emit radiation in the form of UV, in the form of visible light, in the form of infrared, that depends on the temperature of the surface. When the temperature of the surface is that high, like the sun, it can emit radiation, UV light, in the form of UV, in the form of visible light, in the form of infrared, everything. What about radiation from this surface? Is it as hot as the sun? Not really. then what kind of, the radiation this can emit? Only infrared. Then let's talk about the sun and the earth. Oh. So there is the sun. So radiation is coming to the earth. That's the earth, okay? Sun, earth. What is the effective surface temperature? Give me one more minute. It's interesting. 6,000 Kelvin. What is the, the average temperature of the earth? I'm not talking about the temperature inside. What is the temperature of the earth's surface? It depends, right? The temperature in Michigan, temperature in Texas, they are different, right? Average, let's assume about 300 Kelvin. Reasonable, isn't it? Then, what is the form of radiation? UV, visible light, and infrared, all of them coming to the earth. What about the earth? Can this one emit radiation in the form of UV? No, because of the temperature is low. What about visible light? No, because of the temperature is low. Only infrared. Then I told you that when there is an incoming radiation, it can be either observed, rho reflected, or tau transmitted. So when there is a, the incoming radiation, once they hit the ground, what's going to happen? What this Earth does, just observe it and that's all, like a very greedy surface. Then what's going to happen? The Earth is going to look like a Venus. We all die running, right? To maintain constant temperature on the Earth, we need to return the, the radiation. So when there's a radiation comes, it's going to be in the form of UV, in the form of visible light, in the form of infrared. We also shoot the radiation back to the sun in the form of only infrared. Now there's a problem. Some materials in the atmosphere can affect alpha rho tau. There's a layer called ozone, O3. This has extremely low tau only for UV light. So you can say there's an ozone layer, the protecting us from, the skin cancer. Because when UV light comes, this ozone is going to reflect that because it has a very high rho only for UV. And there is another layer. So this one is pretty good. Can we breathe? No, you don't want. It's toxic. However, this one can reflect UV light. So it protects us from, the skin cancer. And there's another layer. It's called carbon dioxide. This one has very low. Oh, that should be tau. Oh, my bad. So it has a very low tau. So this UV light cannot penetrate through. Only for UV light. And this carbon dioxide has very low tau. Only for infrared. Then what's going to happen? UV has been blocked. Or visible light can come through. Infrared can come through. Now we have a significant amount of sunlight. So let's return back to the space to keep the same temperature on the Earth. But our temperature is low. So the only way we can, shoot radiation is going to be in the form of infrared. So infrared is going out. Oh, there's a carbon dioxide. Doesn't allow, the infrared to go outside. So this one return back to the Earth. What is it called? Greenhouse effect. In other words, global warming. That global warming is because of the alpha rho tau due to the, wavelength specific alpha rho tau. That's the reason why global warming happens when we, emit a lot of carbon dioxide. So it works exactly how ozone layer works, but differently, but for different wavelengths. So this one only works for UV, and this one only works for infrared. And unless the Earth can have this much high temperature, we need to rely on infrared, and this carbon dioxide is going to block this infrared to go outside. That's why the temperature keep going up. Okay. Anyway, there are lots of the very interesting the topics to discuss in radiation. However, we don't have time. So if we can finish convection early in December, then we can spend maybe 1 or 2 days to discuss radiation. Okay, that's my plan. Any question? Yes. 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 Oh, yes. Thermodynamically, yes. If you study thermodynamics, that's the only explanation. If you talk about, the electric engineering or, the nuclear engineering, chemical engineering, I don't care. As long as thermodynamics and heat transfer, that's what happens. Because this, the wavelength specific alpha rho tau, it's already proven. And that's how we run solar power plants. That's how we develop UV protected film, sunglasses. That's all wavelength specific, the surface treatment to change alpha rho tau. If that global warming is not true, then your sunglasses should not work in that way. Okay? So that's everything. And let's talk about conduction heat transfer. So today we are going to talk about, how we can come up with heat equation by using Fourier's law. So Fourier's law is simple. Fourier's law is simple. A heat transfer in a certain direction, let's say x, by conduction. Can be determined by minus Ka dt over dx. That's Fourier's law. Then let's talk about heat transfer in a small volume on this cube. Which is this one. Oh, I wish that, I have a much larger screen. Then, can we apply conservation of energy principle? Yes. What is the conservation of energy principle? When you eat 5 hamburgers in the morning, when you put 3 hamburgers in the afternoon, how many hamburgers in your stomach? That is energy balance equation, right? This time, let's assume that your belly can create hamburger. So that is energy generation here. So the energy balance equation for this control volume is going to be energy transfer into this control volume minus energy transfer out of this from this control volume plus energy that can be created by the cube should be the same as the change of energy of this system. But these are energy transfer. In heat transfer, we study the rate of energy transfer, not just energy transfer. Then what is the rate of energy transfer? We can divide by time. So we put that on top of it and divide by time, dt. So this is the energy balance equation for this cube. And there are three directions. This one is a Cartesian coordinate system, x, y, and z. So we can, apply this energy balance equation in x direction, in y direction, and z direction. So let's do that. What kind of heat transfer we can come up with? Let's say this is a solid, so there is only conduction. Then what is the conduction heat transfer? According to the Freel's law, the conduction heat transfer in x direction is going to be minus Ka dt over dx. Okay, then let's talk about this in x direction first. So where is x direction? So there's a x direction, q of x. That q of x is going to be minus Ka dt over dx. So x direction minus Ka dt over dx. Okay, no problem. And there is an outgoing radiation on the other side, qx plus dx. What is dx? The distance in x direction. Then how do you determine this qx plus dx? We do not know, but that should be different from 2x, the incoming, the conduction on the left-hand side. If they are the same, there is nothing changed in the middle, right? So if there is any change in the cube, then means there is a difference between incoming conduction and outgoing conduction. Then how can you approximate the outgoing conduction? We can use the first two terms of Taylor series. You remember what is the Taylor series? Yes. So what is the first two terms of the Taylor series? So qx plus dx. We are going to use the first two terms of Taylor series. The first term, the same as this one, minus Ka at a dt over dx. No problem. Now the second term is going to be the first derivative of the first term with respect to x times dx. So the second term is going to be the first derivative of this one, minus Ka dt over dx, let's say partial t over partial x times dx. That's the second term. So let's say this is partial, because it's three direction, x direction, y direction, and z direction. So then this one too, partial differential equation, because it's not just x direction. Now we have x, y, z. So that is the incoming heat conduction. This one is the approximated outgoing heat conduction, only considering the first two terms of Taylor series. So let me write this one here for this outgoing heat transfer. So this outgoing heat transfer, we have a negative sign minus this one, minus Ka partial t over partial x. So this is partial, plus the second term, partial over partial x minus Ka partial t over partial x times dx. Oops. Oh, It's a surface tension because of my fingers from this mocha frappe. Oh, it's a caramel frappe. Yeah, right. So this is surface tension, right? What about energy generation? I do not know. So let's just assume that the volumetric, the energy generation, heat generation per volume is Q dot. I'm going to say, the heat generation Q dot per volume, so per unit volume. Then what is the unit volume? dx, dy, dz. Unit volume, dx, dy, dz. That is heat generation. Is going to be what? The change of energy over system. Then how do you determine the change of energy over system? If it is a pure solid, we can use specific heat. How do you determine total energy change of the system? We can use a specific heat, mass times specific heat times temperature difference, right? It is dE over dt. Okay, dE over dt. dE over dt. dt. So mass times specific heat dt, the temperature over the time is going to be the change of total energy in the control volume. So I'm going to put this one to replace this. Mass times specific heat dt, but this time partial differential equation, because we have x, y, z, and t. Partial temperature over partial time. So that is energy balance equation, x direction only. Now, this heat transfer can be not only x direction, but y direction and z direction, right? So let's consider energy transfer in and energy transfer out in the y direction and in z direction too. So what is y direction? The same thing, minus Ka partial t over partial x, no, y. And the second term, the first two terms of the Taylor series in y direction, minus Ka partial t over partial y plus partial over partial y minus Ka partial t over partial y dy. That's incoming and outgoing heat conduction in y direction. Now we have a z direction too. Is it new? No. Minus Ka partial t over partial z minus Ka partial t over partial z plus partial over partial z minus Ka partial t over partial z times dz. So this is the energy balance equation. Now we have something in common. Ka partial t over partial x. We have a minus. Minus minus become positive. Plus Ka partial t over partial x. So these two are the same with different sign. So you can cross these two, cross these two, cross these two. And we have a negative, 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 negative become positive. So this one, this one, this one, this one, this one. There are 5 terms in this equation. So this one first, partial over partial x. Ka. Then what is this area? This area is the cross-sectional area in x direction, right? So how do you determine this area? dz times dy. So this area is going to be dy times dz. and partial t over partial x times dx plus the second one, this one, partial over partial y, this time k times area. What area? Where is y direction? This is y direction. And the cross-sectional area is this one. How do you determine this area? dx times dz. dx times dz times partial t over partial y times dy. And the last one, plus partial over partial z k a. What kind of area? Where is the z direction? This way. What is the cross-sectional area? This one. How do you determine this area? dx times dy. dx times dy, partial t over partial z times dz plus here q dot dx dy dz is going to be this one, mass. By the way, mass can be density times volume. Density times, what is the volume? dx dy dz times specific heat Cp times partial temperature over partial time. So this is the energy balance equation. Now, dx is constant, dy is constant, dz is constant because they are the dimension of this cube. So if you look at this one, we have a dx, 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 dx. We have dy, 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 and we have dz and dz, 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 dz. Then what do we have? This energy balance equation becomes partial over partial x, k partial t over partial x, plus partial over partial y, k partial t over partial y, plus partial over partial z, k partial t over partial z, plus q dot, which is the heat generation, is going to be rho Cp partial temperature over partial time. So this is the general heat equation in Cartesian coordinate system. This is what you need to write down on your formula sheet. I'm sorry, there was too much mathematics, right? Then do you need to memorize them? The process? No, just write this one on your formula sheet, okay? We are going to study that equation to solve any problem in chapter 3 and chapter 5. And what you need to know is we got this heat equation by applying conservation of energy principle on this, the small control volume using Fourier's law, assuming that there is only conduction heat transfer. Rho is the density. So we have a mass on the right-hand side. We calculate the mass by density rho times volume, because volume is dx, dy, dz. In that way, we could simplify these equations, right? So the way that we derive is not that important. You just need to know that this is not out of the blue. We use the energy balance equation and Fourier equation together. So that's how we got this heat equation in Cartesian coordinate system. What we need to understand is this is the heat equation in a differential form. Then there should be heat equation in another form. What is the other form? Vector form. Do you like vector form? No? Here is the vector form. I'm pretty sure that you don't like this. You don't like this vector form, right? But if you know how to read this vector form, it's very easy. Okay, let me explain. Give me 5 minutes. Maybe 3 minutes. You will have a complete understanding how to use a vector form. You just need two: gradient and divergence. What is gradient? This upside down triangle is a gradient. What is divergence? Upside down triangle and dot. Divergence, gradient. That's all you need. Then what is gradient? It's simple. Gradient means please replace this upside down triangle with this one. Partial over partial x times, this is the x direction. So unit vector I plus partial over partial y, this is y direction. Unit vector j plus partial over partial z, this is z direction. Unit vector k, that is gradient. So if you have a gradient t, what does it mean? Please put this t here, here, here. So if you see upside down triangle t, that means this one t, this one t, this one t. That's what it meant. Is it hard? Gradient? No, it's not hard. Now, what about this divergence? Oh, it looks similar. We have upside down triangle. So let's talk about that one first. How to interpret this one? This here. So we have upside down triangle. So that means partial over partial xi plus partial over partial yj plus partial over partial zk. The same thing. Whenever you see this upside down triangle, means that this form in Cartesian coordinate system. So we have an upside down triangle here, and we have a t. So that's why we put t here. Now, what is this dot means? It's a dot product. So that means multiply this upside down triangle and this upside down triangle. However, you only consider I times I, j times j, k times k. That's dot product. What about I times j? Oh, get rid of it. I times k, get rid of it. That's a dot product. You will love this dot product. So since we have a dot product, or we have a k in front, so let's put k, 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 and now multiply this gradient, upside down triangle, multiply this and this, because we only consider I times I because of this dot product. This one, partial over partial x of this one, k partial t over partial x. What is I times I? 1. That's all. What about j? Since it's dot product, we only consider j times j. We don't care ji, jk. They're all 0. So j times j only. Partial over partial y of this one. K partial t over partial y. What is j times j? 1. Okay, done. Now the last one, k times k. Since it's dot product, we only consider k times k. We don't care kj, ki. So k, partial over partial z of the last one. K partial t over partial z. What is k times k? 1. So that's what it meant, the first term. Plus heat generation. Plus E dot, oh, I'm saying Q dot. It's going to be rho Cp partial temperature, partial time. So this vector form means this one. Now let's compare this one and this one. They're the same. So that's how you write this heat equation in a differential form, in a vector form. I don't like this tip. Then now, the main question is going to be, okay, I got that. This is the heat equation we are going to use. Now, we are engineers. Are we going to use this, the heat equation in this form? No. What do we like? We like simplification. So let's simplify this equation. How can we do that? First, this is a second order partial differential equation in x, y, z, and first order time, the time differential form on the right hand side, right? So what is the easiest way to simplify this equation? Are you okay with this partial differential equation, x direction, y direction, z direction, and also time dependent? We don't want, because it looks too complicated. Then what if I say, first of all, this k, this k bothers me. It's inside right here. It burns me. So what do you want to do? You want to get rid of it, right? How can you get rid of it? How can you take this one out of this differentiation? You can say k is constant. Can we do that? Yes, unless there is a significant temperature difference from 0 Kelvin to 6,000 Kelvin. Usually heat transfer takes place in near temperature range. What about heat transfer from this classroom to the outside? Here is about 20 degrees Celsius. Outside minus 200 degrees Celsius? No, 10 degrees Celsius. How much K value change between here and outside? Not much. Then can we assume K constant? Yes. Then if you assume K constant, this K comes out, K comes out, K comes out. Then can we divide by K? Yes. Then what happens? You can just get rid of this K, get rid of this K, get rid of this K. Then what is rho Cp over K? Oh, there's nothing rho Cp over K. But there's one thing, K over rho Cp. In chapter 1, we studied another, the thermodynamic property other than this K. What is the other one? Thermal diffusivity, alpha. Alpha is K over rho Cp. Oh, wait. Rho Cp over K. K over rho Cp. So rho Cp over K is going to be 1 over alpha. So this one is 1 over alpha. Then the second one. Can we assume that there's no heat generation? Is there heat generation on this whiteboard? Is there heat generation inside this wall? Usually, unless you study electronic systems, we can expect no heat generation. So let's assume that there is no heat generation. Then you can neglect this one. Then what is the energy balance equation? The heat equation becomes this way. Now K comes out. We have a second order partial differential equation. Partial t square over partial x square plus partial t square over partial y square plus partial t square over partial z square is going to be This one 1 over alpha partial t over partial time. So this is the heat equation when we assume constant K and no heat generation. Then, are you okay with this equation? As an engineer, I'm not okay with it. We want to simplify even further. How can you do that? We are considering X, Y, Z. Let's think about, we want to study heat loss from this classroom to the outside. Let's think about heat loss from the cell phone to the ambient air. This one is very thin. So what is the heat transfer direction? If you are the heat and you want to escape this device, then which direction you want to move? You are here, you want to move all the way to the top and then go out, or just go outside? This way. What about all the way to the right and then go out, or just come out? If you are heat, you will choose the fastest way, right? So the majority of the heat transfer in the cell phone is going to be this way or this way. Then, do we need to consider X, Y, Z all together when you talk about heat transfer from the cell phone? No, only one direction. Then can we say one-dimensional heat transfer? Yes. In what direction? Are you going to choose Y or Z? You can do so, but most likely it is reasonable to choose X. Then if we say one-dimensional heat transfer, you can neglect these two. And now I'm recording this lecture, so it is continuously the running, the CPU. So it generates heat continuously. So is it steady state heat transfer or transient heat transfer? Okay, let me rephrase the question. How do we know whether heat transfer problem is steady state or transient? When it is transient, the main property is changing. What is the main property when we talk about heat transfer? The temperature of this cell phone. Do you think the temperature of the cell phone is changing? Now it is about 20 degrees Celsius. If I hold it 5 minutes, it's going to be 6,000 degrees Celsius like the sun. No, the temperature will remain constant. The steady state heat transfer. So when it is a steady state heat transfer, what's going to be on the right-hand side? 0. So if we say this is a steady state heat transfer, you can neglect that, then the energy balance equation is going to be partial t square over partial x square is 0. This is what we are going to study in chapter 3. Oh, I don't think this one is a steady state. I'm going to say transient. So the transient heat transfer, partial t square over partial x square is going to be 1 over alpha partial t over partial t. So this one is transient heat transfer. Where do we study? Chapter 5. So we have 2 chapters to study steady state heat transfer, 1 dimension, and transient heat transfer in chapter 5. So these 2 are the main chapter for heat conduction, and these 2 chapters are those covered by your second exam. Any question? So from this Thursday, we are going to study chapter 3 to learn how to analyze steady state heat conduction. It's going to take about 2 class time. So it will end next Tuesday. Then we are going to start chapter 5, transient heat conduction. That will take about another 2 class time. So it's going to end the Tuesday the following week. That means our second exam is going to come in 3 weeks from now. Okay, that's our plan. Any question? No? Then see you next week. Oh, I mean this Thursday. Thank you.